Okay, we're very happy to have Professor Hiraku Nakajima to tell us about the Coulomb branches of orthosymplectic quiver gauge theories.
Thank you very much for introduction, and I'd like to thank Andrea and Mina for invitation to here. Okay, I give two lectures about Coulomb branch for orthosymplectic quiver gauge theories. So I first start with the quick review on the Coulomb branch in general. I hope many of you already heard about it. But anyway, so let me fix the notation. So G be a complex reductive group. Or if you like differential geometry, then maybe you can consider this compact Lie group. And G is its complication. And then I take its symplectic representation. So symplectic representation means that first of all, M is a usual representation G, but M is equipped with symplectic form, which is preserved by G. Then you can consider corresponding gauge theory, 3Dn equal 4 supersymmetric gauge theory. So basically, you consider the connection, G connection, and also spinors with values in M, and you define certain Lagrangian, and it can make to be supersymmetric, and consider this corresponding gauge theory. Then physicists assign Higgs branch and Coulomb branches to them. And the Higgs branch is easy to understand mathematically, so this is just MH. So maybe I did not buy MH of G of M. So this is defined as symplectic reduction. So I denote M triple slash G. So this is my notation for symplectic reduction. So you have a moment map. And then you take inverse image of 0 and take categorical quotient by G. So this is the definition. The Coulomb branch is more difficult. The Coulomb branch has been considered many years by physicists, but its mathematical definition was not available for many years. And that was given a special case by Berkeley, Finkelberg, and myself, and then later generated to more general case. Anyway, so MC, so this is Coulomb branch. Soft. So you first assume M is the direct sum of N and its dual. So N is a usual representation of G, and suppose M is of this special form. Then you consider the moduli stack, which I denote by keeping the notation in the original paper. So O is formal Laurent power series. R divided by this group. So this is moduli stack of P. This is G bundle over disk. So this is spectrum of O plus, sorry. This is, first I need to introduce Raviolo. Raviolo is, so two disks which is glued along the puncture disk. So the spec. spec of O and D. So this is a formal disk. If you are not familiar with this notion, but you just imagine that this is a disk in complex plane, and whose radius is very small. So this is a speckle. And O is in K. Speckle. So this is a formal puncture disk. So you can regard this as the complement of the origin in disk. So this raviolo, so you have two disks glued, two small, very small disks glued along the puncture disk. You consider this as some algebra geometric S2. So because this is like two sphere. What? Okay. And this, the modular space on raviolo plus n valued sections, holomark section. Uptice model. So this is some modular space. Formally, this is a modular space of gauge theoretic object on S2, but by technical reason, we replaced it by this algebra geometric model. And then you consider its homology. So technically, more precisely, we use the so-called Borel-Muller homology of this modular stack. And you have the convolution product on this, defined on this homology. So you consider three disks glued along the puncture disk. Then you have three projections. 1, 3, 1, 2, and P2, 3. Taking second and third sheet, or first and second sheet, and so on. Then you have a homology class in here. Then you can pull back and then push forward by P1, 3. So this gives convolution product, which is associative. Gives an associative algebra structure on this. And in this particular case, this is commutative. And then you get some commutative algebra from this modular space and Coulomb branch. Or I mean, in physics language, this is called the space of monopole operators. So monopole is some solutions of partial differential equation defined on R3, but it has a singularity at the origin. So that this is a Kariaki for this R3 with singularity. So anyway, so monopole operator form algebra by colliding two monopoles, and it forms a commutative algebra. And then Coulomb branch is defined as spectrum of this commutative algebra. This commutative algebra. And this definition is later generalized to more general setting, which more general case. But not arbitrary. So there is some technical condition, which is usually called anomaly cancellation. So this is due to Weberman, Finkelberg, Raskin, and Travkin, and also Telemann, Konstantin Telemann. So in fact, this orthosymplectic quiver gauge theory is not of this example, of this type of examples. So we need this general, more general definition. And as I said, it is not, Coulomb branch is not well defined in general. So I will explain what kind of condition you need to impose later. So this is anyway. So this is a general definition of a Coulomb branch, and so maybe this modular space is infinite dimension and have very bad singularities, and its homology is hard to analyze. So although this definition makes sense for arbitrary G and M with some additional condition, in practice it is not so easy to understand this Coulomb branch. So people start to study the Coulomb branch in various examples. And in particular, so physicists has been studied Coulomb branch for many years, and they have lots of examples, concrete examples of G and M. Then they can identify those Coulomb branch with some known space, quite often modular space of instantaneous and modular space of monopoles. And somehow we tried. So for several years, recently, I'm trying to reproduce physicists those answers in our definition, or maybe we can define their answers in some cases, and that kind of things I have been doing recently. So most of successful sets of examples is the so-called quiver gauge theory.
Is there a simple reason for why you need to take this radiolo but not P1?
So I in my very first paper, I tried to use P1, but so this if the n is equal to 0, then this corresponding modular space is called affine Grassmannian, and so people have been studied affine Grassmannian many years, and so those our definition use such large literature result in literature. So that's one of the reasons. And yeah, I think I still don't quite understand. I'm very happy if somebody really defined the same Coulomb branch using a modular space on P1 instead. But usually the modular space on bundles on P1 is the most difficult one, because how to say, it is highly singular. So somehow you must understand a good understanding of singularities. Classes, examples of G and M. So that's so far, as I said, the quiver gauge theory. So you start with quiver. So this consists of set of vertices and arrows, oriented arrows. Then you take V and W, two graded vector spaces. So for each vertex you have, yeah, maybe I just write the notation like this. So you start with G is just a product of general linear groups for VIs. So if you have V1, V2, and V3, and W1, and W2, and W3. Then this is a product of general graph of V1 and V2 and V3. And N is linear maps, space of linear maps for each arrows. So we have, for example, in this case, we have 5 arrows and we have 5 linear maps, and we consider the representations of G given by all such linear maps. And then for M, you just consider its dual space, which means you also add arrows in opposite direction. And then you can consider corresponding quiver gauge theory. And in this case, Higgs branch is called quiver variety, which I have introduced many, many years ago. And the Coulomb branch is not yet known in full generality, but at least for finite type quiver. So MC is the so-called generalized affine Grassmannian slice. So since this result is not relevant in my talk, so I will not explain what is affine Grassmannian. But this is anyway, so for finite type case, this is some known space. And so the relevant in this talk is the following. So in type A, so we have some different description. This is something to do with some variety related to nilpotent cone, nilpotent variety. Or GLN. So then somehow it is natural to ask. So nilpotent variety is a set of matrices which is nilpotent, which are nilpotent. So you can also consider nilpotent variety for other real algebras. Maybe this is GL. So for example, for classical groups, classical real algebra SOISPs, you can also consider the corresponding nilpotent orbits. Then you can ask how those are realized in terms of the Higgs branch or Coulomb branches. That is a natural question. And of course, you can also consider replace, so this is type A, and this, even if, maybe this I should say, in type AM, so this N, or maybe this is SLN. So this N and M are not the same, so they in general different. So anyway, so you can also consider change the quiver to other types. And this result, as I said, is true, remains to be true arbitrary finite type quivers. And in that case, affine Grassmannian is defined for, oops, I don't want to block this. I don't want to break. So this G, affine Grassmannian is defined for the group, the complex reactive group. And this complex reactive group is defined by quiver. So it's different from the original G. And as I mentioned, in this modular space is closely related to affine Grassmannian. But this affine Grassmannian appeared in the definition of Coulomb branch, and the resulted affine Grassmannian here are different, no relation at all. But anyway, so I just want to say that if I replace this type A by type D, then you get affine Grassmannian for classical groups. But it's not related to nilpotent orbit. This is something different. In type A, by some miracle, you have both affine Grassmannian and nilpotent varieties are related, but they are different varieties. So anyway, so this kind of variance for quiver case, you can consider many cases, different variations, like replacing type A by classical types, classical type D diagrams. But today and next week, I'm interested in the generalization of this algebra to classical diagrams. Any questions?
This Coulomb bracket will always be
yeah, maybe, yeah. I should say several properties. Yes, thank you for asking. So, first of all, so this MC, so properties, some properties. So you have natural deformation quantization. So you have C-star action on the formal disk by rotation action. Then you can consider equivalent Borel-Moore homology. And this still has convolution product. And this is no longer commutative. This is non-commutative. I don't explain why it is commutative. Some in 3D pictures, so you have singularities, and there's no ordering if you plot singularity in three spaces. But if you consider C-star action, which means that you have, so you decompose R into C cross R, and this C-star acting on C. So somehow it must sit on the origin of C. The singularity, if you want to have the C-star equivalent moduli space, then the singularity sits only on the axis. So then you have ordering. So that is the reason why it is not commutative. So this is the deformation quantization of the coordinate ring of the Coulomb branch. And in particular, you can define the Poisson bracket. So you have a function f and g, then define its consider first you consider its lift to deformation quantization and take the commutator, then divide by h bar. So H star equivalent homology of a point of C star is polynomial in one variable, which people usually denote by h bar, and then take h bar to be 0. So this is well defined independent of the choice of lifting, and it defines a Poisson bracket. And it is known that this Coulomb branch, if you take the regular, it's smooth locus. This Poisson bracket is symplectic on this. So this is the first property, and also you have the equivalent homology of point. So this is point divided by 0.4. So since the space is the quotient stack, So you have the structure homomorphism from H star RGO. So the spectrum of this is MC, and the spectrum of this is known to be T divided by Weyl group. So T is the real algebra of the maximal torus. And the W is Weyl group. So you have a morphism in the opposite direction. And you can show that MC is equipped with this commutative diagram. So you consider T cross T check. T check is a dual torus to this maximal torus, and divide by. And this is the first projection. And this is birational. And in particular, if you consider the generic fiber of this morphism, so then it is the dual torus. In particular, so for example, this says that Coulomb branch is dimension of Coulomb branch is twice of the dimension of the torus. And also it says, as I said, so the generic fiber of this morphism is a torus. So this is T is a half dimensional in the Coulomb branch. And this is algebraic integrable system. So this is a how to say what? So this is a commuting. So Poisson commuting. So if you have a function defined on here, and then pull back and take a Poisson bracket given by this, then it commutes. And that is basically because this homomorphism extends to deformation quantization. So in deformation quantization, we have the equivalent homology of GO times C star, and this is a commutative subalgebra in deformation quantization, and in particular, if you consider this Poisson bracket, it vanishes. So each fiber of this morphism are Lagrangian. And so this structure, in fact, plays an important role to understand the geometry of Coulomb branch. Any other question? Yeah.
So sometimes people restrict to this quiver, general quiver, the fear of singularity. Can comment a little bit. In general, in one case you have a smooth resolution. In some case,
resolution. For the Higgs branch, it has been known that instead of, maybe I erased the definition. For the Higgs branch, so I don't explain what I really mean by this double slash. But this is the so-called categorical quotient. So which means you consider the ring of functions on this level set and take the G equivalent set and take a spectrum. So this is the definition of this categorical quotient. But you can, if you have some character, then you can consider, instead of invariant, you can consider semi-invariant, which means that, so if you change the function by the group element, then it is multiplied by this, according to this. Some powers of this character. So this is called GIT quotient. So from semi-invariant. And in this, by this construction, you can construct the resolution of singularity for Higgs branch. But for Coulomb branch, so you should use the so-called flavor symmetry group. And so yeah, maybe this is a continuation of the properties. So return back to general case. So you have G and M. And if you have a larger group, G tilde, which contains the original group as a normal subgroup, which again, this representation is extended representation of G tilde. And assumed G tilde divided by G is torus, which is flavor torus in physics literature. Then you can consider the Coulomb branch for larger group. Then, so computing the dimension, this is larger than the dimensions of MC by 2 times dimension of TF, because this is dimension of T is twice of the dimension of T was the dimension of Coulomb branch. So in order to recover so in fact, you have the action of the dual torus of the flavor symmetry. And if you take the reduction by TF check, then you recover the original Coulomb branch. So this is one of the general property of the Coulomb branch. So you can take the GIT semi-invariant like this. Then you can sometimes define GIT quotients. And in type A, this gives a resolution of singularities for generalized affine Grassmannian. But in general, for type DOE, if so you have two vector spaces, and if dimension vectors of doubles is the so-called the sum of minuscule. Minuscule weights. So which means that what it means. So for you consider the Dinkin diagram type. So then you consider the coefficients of highest root, and you have twos and ones, and the minuscule weight mean that those vertices, fundamental weight which correspond to those vertices whose coefficient is 1. And if W has non-zero entry only in those vertices, then you can resolve in this way. You can take the resolution. But in general, if you, this consideration makes sense for in more generally, but that is only partial resolution of singularities, not the full resolution in general. So you need to still have some singularities. And this is somehow related to, so in the Higgs branch side, you consider, so if you have a flavor symmetry like this, then you have the corresponding torus action on the Higgs branch. And you consider the torus fixed points. And if this is isolated point, then this happens in type A, the fixed points are always isolated. But for type DOA in general, it is not. And if, as I said, if this is W is a sum of minuscule weight, then this is fixed point is isolated, but not in general. And somehow.
Maybe what you meant, if the quiver is not of 80 type, so far, if the quiver is of 80 type, one definition of a minuscule representation is that all the weights are in the single orbit. Is there an analogous definition for an ordinary quiver? For an arbitrary quiver?
You mean that when we have the resolution singularity?
It plays the same role. Equivalently. It's something of guarantee.
But for affine type A, we can construct resolution singularities, but we need additional flavor symmetry which comes from the cycle. So for type A diagram, you have is like this. You have a cycle, and if you have a cycle, then you have one addition. So the source of the flavor symmetry is just the general that maximal torus of W's, those frame vector spaces. But for this particular case, you have one additional flavor symmetry that can be used to construct the full resolution. But for other types, you don't have that, and I don't study when it has. My guess is that there's no there are no resolution in general in other. Yeah, that's and because first because there's no such cycle, and even for affine type A, if you don't use this additional flavor symmetry, you cannot construct resolution singularities. So anyway, so maybe I mentioned that. So those also symplectic quiver gauge theories are some variant of this quiver gauge theory, but there's the flavor symmetry group is very small. In fact, you can define larger G tilde, but the quotient is just a finite group. So you cannot construct this kind of larger space. And also what? So you have this. I used for the Higgs branch. I used this character, but you cannot have this co-character in orthosymplectic. In that sense, many tools which has been used in analyzing quiver gauge theory are not available for orthosymplectic. In that sense, I think that those orthosymplectic quiver gauge theory is interesting. And as I said, this is something related to nilpotent orbits for classical types. Let me go on. So this, from now, this is joint work in progress with Finkelberg and Hanany. So in order to motivate the definition of orthosymplectic, I start with the ADHM description of instantons on alpha. Or maybe you can consider this is a special case of Jordan quiver. You have one vertex and one loop. So in this Jordan quiver case, what is Higgs branch concretely? So you have, so I use this notation, K and N. And you make a double. So I have map A and B and C and D. So Higgs branch is A, B, C, D. By some reason, I use capital C and D for those linear maps. So the moment map is this commutator of CT plus AB equals 0. So this is a map from static. This is a K. This is a notation for K-dimensional vector space, and this is large N-dimensional. And this is known to be moduli space of maybe unitary UN instantons alpha. Or more precisely, this is the so-called Uhlenbeck partial quantification. And this is the famous the result about the Drinfeld-Hitchin-Manning. Then, so this ADHM description has a variant for classical groups instead of unitary groups. They consider SO so I denote this in this way, SON. So for SON to n instantons, so this framed vector space is replaced by Cn to the Cn with symmetric inner products. But so I just denote the corresponding group. And then you have this, and for this sp2k, and I have this one. And I impose the condition that d equal minus c star. No, sorry. So this is too early. Oh, C star is equal to C and D star is equal to D and B equal to minus C star. So same equation and still CD. And then take the symplectic reduction by SPO2K. So the proof of this result is just somehow combination of this result together with the observation that so SON instanton mean that SON instanton is in particular UN instanton, and you have the symmetric bilinear form. So in particular, the instanton is isomorphic to dual instanton. So this dual instanton. And so you just look at what is the corresponding linear maps A, B, C, D in terms of for the A star, and those two descriptions are isomorphic. That is a requirement. And then you see this. This is a little too brief, but this is well-known result. And one interesting feature is that, so if you consider the SON instant, then the gauge vertex is SP. So SO and SP are interchanged. If you consider SP instant, then this will be orthogonal. And that is, I mean, this is, of course, as I said, if you write down the proof of this statement, as I sketched, you get SP or orthogonal. But one way to understand is that this is again symplectic reduction. So if you consider the space of A's, for example, maybe this is not separated. So this means that C to the N and the C to the 2K, and you have symplectic form. This is orthogonal form. And if when I take the adjoint, then I use these forms. Or is symmetric form. Non-generate, so A B is equal to X, Y is equal to YX, and non-degenerate. So B, from this equation, B is determined from A. So space, for example, space of A's is a tensor product of Cn, maybe this is home of Cn to Ck. Or Cn, because we have non-direct form, this is Cn tensor with Ck. And this is symplectic. And this is symmetric orthogonal. C to K. So then you have the form which is given by tensor product. So this tensor product is symplectic. So if both are orthogonal and orthogonal, then the tensor product is orthogonal. So then this is not a symplectic vector space. So similarly, so if you put this, then this is a symplectic vector space. In this case, it's clear. D and C are dual to each other. But anyway, so the space, so this is again M is the space of those, this one. Maybe M for SO10. So the modular space, modular B, SON instantons. So this is symplectic reduction. So in particular, this should be symplectic vector space. So orthogonal. If this is orthogonal, then this should be symplectic. And this, if this is symplectic, then the opposite one is orthogonal. Yes?
So what if we gain one more dash from Coulomb?
Pardon?
There's two slashes and it's not three slashes.
3 slash means the symplectic reduction, and 2 slash is a categorical quotient. And if I just write one slash, just means is a quotient slack. Yeah, without equation. Sorry, without this equation. This is M also. And this is a momentum. And one delicate point is that M of SPN so you consider the SP2K instantons modular of SP2K instantons is MSP2K divided by orthogonal. Maybe this is 2, sorry. Maybe I switch to N and K. So if you replace S of K, then the Higgs branch is different in general. So this is a delicate point. So you must be careful about the choice of the gauge group. And this replacement just in the level of quotient space. So if the action is not this determinant -1 element acts non-trivially on the space, then it means that if you replace by this, then you get two double cover of the instant modular space. So this is an interesting point, and in fact, so people have been studied similar phenomena in nilpotent orbits for classical types. And the Coulomb branch simultaneously in the same way. Coulomb branch could be also different for other types. Okay. So the first of our result is the Coulomb branch. MC of, so the group is, so SON instantons. So it means that we consider the pairs of this representation. So in fact, this is not well defined by anomaly cancellation condition, by anomaly. If n is odd. And if this is even, so this is symmetric power of type D and prime surface. So Sk is symmetric power. K is symmetric power, which you take, this is a surface, and so you take the case product of surface, case Cartesian product, and take the quotient by symmetric group. And the n prime surface is a hypersurface singularity. So this is C square is delta eta square delta n prime minus 1. If n prime is positive, and C square is delta eta. So people usually consider the dn prime surface when n prime is greater than or equal to 4. I mean, this is very famous AD type singularities. But if you write down the equation, then it makes sense for n prime smaller than 4. And we take the type dn prime surface as defined in the same equation. So this is our first result. And proof of this statement, maybe I also write. If the n prime is greater than or equal to 4, it is. I mean, after change of some possibly change of value coordinates, this is type dn prime surface. Second case, this is first case. MC of O of, maybe I will change the slightly. OK to K plus, O to K plus, or to K plus 1. Because that is something, yeah, so anyway, maybe I did. So those numbers are not so important. But anyway, so we get the symmetric powers of type D surface. So that is the result. And I think this example has been known in physics literature, but I'm not sure who first observed this. And anyway, so in our approach, so we use this. We have this diagram. So in order to show that this right-hand side is isomorphic to Coulomb branch, the first step is to construct birational isomorphism in here. This is the first step, and I don't explain how to do this. But yeah, many things are known for this symmetric powers, and this is not so difficult. And the second step is step 2 is just the symmetric power. This Sk of type D is a normal variety. Well, maybe step 1 is the construction of this morphism also. and this is algebraic integrable system. In particular, the fiber is torus, algebraic torus. So this is step 2. And the step 3, so you consider the base of this integrable system, and this has some root hyperplanes. Yeah, more precisely what we call generalized root hyperplanes. So maybe I didn't explain how to construct this structure. So, but MC is a spectrum of some quotient stack. And this structure is coming from the structures of the equivalent homology. And I said that this is the equivalent homology point. And you replace this GO by maximal torus and study the fixed point in R. And those root hyperplanes. So, and then you take the co-character in this torus and you study the various fixed points. And fixed point in general is some discrete spaces. But if you hit on those generalized root hyperplane, co-character hit on generalized root hyperplane, then the fixed point is larger. So by studying those equivalent geometry of this modular space, you can somehow see this picture, and also you can slightly more finer picture, which is a description of those space which happens on this single root hyperplane. So this is technical part. Step 3 is analyze what happens. So if several general root hyperplanes intersect, then it is difficult to understand what happens in the intersection point. But if you just co-character sits on a single generalized root hyperplane, then you can study what happens. And then that implies, from that you can show that by combining this, you have the birational morphism, and this birational morphism extends on the complement of the intersection of two hyperplanes, two or more hyperplanes. Then by normality, it automatically extends. So this is a rough strategy of that. So anyway, so the proof is not illuminating at all, unless you have the candidate. What you a priori know what should be the candidate of the Coulomb branch in advance, and then you check. Unless you check all those properties, you cannot prove this result. So in that sense, somehow we need some guess what should be the Coulomb branch in the beginning. Yes.
Going back a little bit, can you elaborate what you mean by a Coulomb branch isn't well defined by anomalies? Like, is there just no supersymmetric NPD n equals 4-3 with that H movement? Or
you can put the chance, but so I don't put the chance Simons, and so I So we usually understand in this way, in the following way. So maybe this is not, I mean, maybe I should explain. This is a result of the analysis of anomaly. So we have G, and because G has a representation, symplectic representation M, so you have a symplectic group for M. And having symplectic representation means you have the group homomorphism like this. And then you consider the fourth homotopy group. And I'm not algebraic topologist, so I don't know how to understand this, but it is known to be this is plus minus. And this homogeneity vanishes, that is the anomaly cancellation. And in this particular case, so n odd means that this is minus 1. So it's this violates this condition. Let me see. Maybe yeah, I should explain this result. It's already known. So the original case is K and N, and this one MC is symmetric powers of type N minus 1 surface. So this has been proved earlier. Yeah. So roughly you can consider the instantons on this kind of surface, which is maybe in good case this is the C2 divided by finite subgroup of type ADE, and the gauge group and the finite group are exchanged for Higgs and Coulomb gauges. So this is compatible with this first result. So in this case, SO2n is type Dn, and I think SO2n prime, the corresponding linking diagonal type Dn prime, and so this is the instanton of the gauge group. So and the finite group is a trivial group in this case, and that is the reason why we get the symmetric powers. But for other groups, so for sp2n is type Cn. So this is Cn, and there's no corresponding finite group. And I mean, of course, there's some variant of this AD classification for finite by Slowly, finite group of SL2 by Slowly, but I'm not sure. And also this n and n plus 4, maybe I don't remember. Maybe, and also I should also mention that. So here, if you like the quantization, deformation quantization, then I think this is already interesting case. So as I said, so Coulomb has a natural deformation quantization by considering the C-star equivalent homology. And in particular, you can consider the corresponding quantization. And so type A case, so this has been proved by my joint work with Godera. So in this case, Sk of type n minus 1 is quantized to the so-called spherical part of rational Schrödinger algebra. So this you consider corresponding group G of NG and take K copies and take Sk. This is symmetric group. And the type Dn, MC of SP of 2K. of M of SO2n. So this is again same just. So this this is replaced by type D group, type Dn group. And take k times and sk. At least if n is larger than 4. And in particular, if n is equal to 4, then this is so-called the rational version of C Daha. C energy. No CK. So this McDonald has a general definition for Daha for associated with affine root system, which may not be reduced, and this CHC is one of the most interesting Daha among all those classifications. And corresponding McDonald polynomial has 6 parameters, and it's specialized to many other McDonald polynomials. Ask you some polynomial in some special case. Or I don't remember that. And if n is greater than 4, then I'm not sure anybody seriously studied corresponding Cherenkov Daha. Or n equal 1 and 2 and 3, I'm not sure what has been known. Okay. Any question or comment? So this is a very non-illuminating argument. So in general, there's some expectation is moduli space of G instantons on so you consider a pair of AD groups, G and G prime, and you consider modulus. And so if M is Higgs branch, so if Higgs branch, if this instance of modular space has ADHM type description, and if G is classical, we do have. And you use M on this group and symplectic representation by this ADHM description. Then expectation is MC is something like you exchange G and G prime. So this is the case when gamma G prime is a trivial group. Trivial, or I mean, this is U1 gauge theory. U1 gauge group. And G is the corresponding. Maybe this is excluded. So I go back to this one. SP2K and SO2N. And this G is SO2N, so then corresponding gamma G is type D group. And modular space of instantons. U1 instanton is symmetric powers. And this is one way to guess this should be. But for this case, it's not so clear why we have. I don't have any good, I mean, except the just, first of all, in order to guess what it is, so somehow this surface is independent of K, which means, So we put some group or k to k or to k plus 1.
But somehow this GN also sort of has to be different than special case of that.
This is not related at all. This is a different gauge group and different. So surface is the same. Yeah, surface is the same. But we also know that in particular k equal 1 case, the Coulomb branch is dimension 2, and we have the classification of the Coulomb branch for the case of surface. And this is either type A surface or type D surface, or C, some variants, small variants. And so because of this reason, we don't have much choices. So this is the same. Say, I mean, if m prime is equal to n plus 4, this is the same surface, but that is just coincidence, and I don't have any conceptual explanation. It's just because it is known that the Coulomb branch, surface Coulomb branch is either type A or type D. That is my understanding. Okay, I'm a little bit tired, so maybe I just motivate a definition on the orthosymplectic quiver gauge theory, and then I stop. How many minutes I already talk? It's almost 1.5 hours, so it's okay to stop soon. So last week, it was 2 hours talk, but I'm afraid I cannot do. 1.5 is already too long for me. So we consider the SL2 or SU2 equivariant instantons. So I identify alpha with C2, and you have the natural SL2 action on C2. And I consider the pullback by this group action, and I assume that equivalent instanton means that this pullback is isomorphic to the original instant. So this is SL2 equivalent instanton. Then it means that V, and maybe, so we call this, we have maybe K, I cannot this one, OK, and SP1 to N. So I denote this vector space, so corresponding V is C, okay, double. Then V and W are, because of this reason, SL2 representation. And CD, AB, not the strict sense, but in some sense intertwined. SL2 action. I hope this is natural. So if you consider SL2 equivalent instantons, then those vector spaces is inherit with SL2 representation, structure of SL2 representation. So then, so this V, this vector space V, decompose into irreducibles. So rho I is I-dimensional irreducible representation of SL2. And similarly for that one. And if V is orthogonal, then each summand must be orthogonal. But rho I is a irreducible representation by SL2. So in particular, if I is odd number, then rho I is symmetric. And if I is even, then Vi is symmetric. I hope I am correct. So Vi or I odd is orthogonal, and Vi or I even is symplectic. Right? And similarly for Wi's. So you have orthogonal and symplectic alternatively. And then so in fact, the linear maps is like this following. So you have V1 and the W1. So those small a and small b's are just intertwining SL2 action as usual. This is A1, B1, A2, B2, and V3, W3. And so on. And the C and D are somehow you should combine C and D's, and they form represent two-dimensional representation. So you consider the cleavage Borden. So this is rho I minus 1 plus rho I plus 1. So the C and D decompose into those. So you get the type A quivers in this. This is C and D, C and D. And the rule is for C and D, because of this rule, is slightly different from the previous one. B equal minus S now, and D equal minus S. So then you can define the group G to be product of which is odd O of V of I odd times I even SP of Vi, and M is the first framing card is Vi tensor Wi. Maybe I should say that for V and W in the original diagram, I emphasize that if one of the group is orthogonal type, the other group is symplectic, orthogonal and symplectic. And then it means if Vi is orthogonal, then corresponding Wi is symplectic. So this is product of orthogonal and symplectic, or symplectic and orthogonal. So anyway, so this is always symplectic vector space. A and B, little one, no. A and B are just, I don't have a good explanation. So it is about the representation. So we have home of V and C2 tensor B. So this is C and D part, and we have home of V W. So in the original, I think this is a usually. And so unless you have how to say? So those symmetric or symplectic home are defined after taking the how to say, SL2 invariant ones. And you need to understand what should be the SL2 action on here, on the original space. And SL2 acts only on here, not on this. Because you can, unless you identify W with W star, well, this is already V and V star and V, then you cannot identify this with this. What is? Yes. Maybe. And once you arrive at this definition, then also symplectic Weber case. Is defined for bipartite graph. So bipartite graph means that you have orthogonal vertex and symplectic vertex, or maybe better write plus or minus, maybe like this. So each vertex has either orthogonal or symplectic type, and if edge is connecting two vertices, then one is orthogonal and the other is symplectic. And if this is the first one, first integrated, and V is equal to Vi, and the W is Wi, and V, if I is plus type, orthogonal type, then Vi is orthogonal, and minus type, this is symplectic, and so on. So it's not necessary. You don't need the graph, underlying graph is not of type A, so you can consider marginal. And if you have edge loop, then you can, like in the case of Jordan quiver, you can also consider the self-adjoint homomorphisms. Right, then you just define G and M in the same way. But also, so in some cases, one can also replace O of Vi by special orthogonal way. So as I mentioned, you have, so in the AGHM description, we usually take O of Vi, but you can also consider SO. And maybe I didn't say that. So in this particular example of Jordan quiver, if I consider S of O, I of 2k plus minus 2k plus 1. So for all the case, I think the Coulomb branch is unchanged. But if this is S of 2k, then the Coulomb branch is double cover of this one. So I'm not sure this what it means, but this is just the checking. For this particular case, it's a type A graph. Type A graph. And starting from either plus or minus. You have two cases. V1 is either orthogonal or symplectic.
What's the ramification divided over the What's the ramification divided over the double power?
Ramification divisor of the that I don't study. I think I don't know that. That is let me see. So it's so the point is that the while group of SO2K is what? Something like yeah. So this k minus 1, and I'm not sure what is the consensus for orthogonal group, but I think this is. And the classical description of the Coulomb branch, MC is birational to T cross T check divided by while group. So by this you define the while group, and then for special orthogonal group you get the usual while group, and for orthogonal group this is the equivalent cohomology point, and that is this one, and from that I think you can guess what should be the ramification divisor, but I don't consider it.
Do you have some fundamental understanding of way to change it, or I know this follows from the brain construction and string theory, but one should also I don't know if this analysis was redone using just organic fold action on AD singularities or A-type singularities, one should be able to do. So if you
yeah, this is I mean, there are several oriented folds, and we choose a particular one. And let me see, how should I define that?
there should be some elementary string theory explanation, just by starting with what you know about.
I mean this kind of.
Yeah, I know. That's not least a couple string theory. That's not kind of thing.
And then so you consider the involutions and. Yeah, I think I forget. So one of the oriented fold involves the symmetry of the diagram, but in this particular case we don't use that one, and somehow for each D3 brane we use the involution, and the diagram is not changed. And we can consider also other variants which involve the diagram automatism. For example, instead of SL2 equivalent instantons, I consider the S1 equivalent one. Then we have very similar result, but rho I, maybe I erase rho I. Rho I is a weight I representation of S1, and rho I and rho minus I are dual to each other. And in that way, you can realize the involution on the diagram.
plug it in.
Yeah,
Of course.
I mean, of course,
that's the answer to my question.
Yeah.
It was actually not a good question. Great. Yeah, that makes sense.
Is there some anomaly translation tradition of the
There's an American, so I will explain next week. But so you have the symplectic vertices, then you consider the nearby vector spaces and consider the sum of dimensions. Then that must be the even number. That is a condition, like in the Jordan quiver case.
What is this is the definition of orthosymplectic quiver.
Also symplectic quiver case. Yeah. This is example all of those so that I motivated this definition. Yeah, by considering SL2 equivalent ones. Okay, maybe let us stop. Thank you for attention.
Yeah.